Introducing our next speaker, it's my pleasure to introduce Professor Clint Schow, who is at UC Santa Barbara. And Clint received his BS, MS, and PhDs from the University of Texas at Austin. And after positions at IBM and Agility Communications, Dr. Schow spent more than a decade at the IBM T.J. Watson Research Center in Yorktown Heights, New York, as a research staff member and manager of the Optical Link and System Design Group. He's led international R&D programs spanning chip-to-chip optical links, VCSEL and silicon photonic transceivers, nanophotonic switches, and new system architectures enabled by high bandwidth, low latency photonic networks. And in 2015, Dr. Schow joined the faculty of the University of California at Santa Barbara. He's been an invited speaker and served on committees for numerous international conferences. He's a fellow of the OSA and the IEEE and has published more than 200 journal and conference articles and has 33 issued patents. Clint, thank you very much. Over to you.
Thanks, Rob. Appreciate it. Sorry, I had to find mute. Are the slides in the right view? Are they presentation?
Yep, we can see it great. Thank you.
Wow, it almost never happens. Well, thanks. I do appreciate it. It always makes me think I need to shorten up my bio, but I do appreciate the opportunity to speak today and the invitation from you and the rest of the organizers. So I'll dive right into it. By my watch, we're right on time. So I'll keep trying to keep the cadence up and keep us on schedule. Most of what I'm going to talk about today is going to be under a program that we've been doing under the funding by ARPA-E, which is part of the Department of Energy. And it's been going on for a long time. So it was conceived in 2016. We went through one phase where it was UCSB and Facebook as the primary organizations working on it. We transitioned out of that. I'm not going to read through these slides, but basically we were looking at a lot of things. It was a co-packaged optics play. We were focused on low power VCSEL interconnects for inside the racks and coherent links for outside of or top of rack and above links. And then we were exploring network architectures that could exploit the coherent links that we were working on. And that's what I'm going to talk about today. We changed a little bit or kind of shifted a little into phase two. We dropped the VCSEL work and we really are focusing on trying to bring coherent optics into the data center, making that a reality. And one of the exciting things is we not only continue to partner with the folks at now Meta, and Rob is one of the leaders of that, but we also brought on Intel as a partner. And so I'll talk about it later, but it was basically the perfect technology platform to try and realize the vision that we have for the brand of coherent optics that we're developing. There are a lot of words on these slides. Again, I'm not really going to read through it. I think I'm going to make all these points in words, and I'll try and make it brief. So I think this is one of those slides that probably doesn't even need to be shown, but for some background, why are we working on coherent links inside the data center? Well, a long time ago, I think we were motivated just by the more traditional intra-data center links, which if you take the Cisco surveys show high compound annual growth rates. That sounds like that's maybe yesterday's news from what we heard this morning, and that the sort of AI/ML workloads are overtaking that. So it's maybe even more important to work on links inside the data center. We see this as fundamentally an O-band operation. So it takes advantage of the zero dispersion point in single mode fiber. And so for links up to even 2 kilometers, you really don't have to worry about dispersion as a primary limiting factor. And that's fundamentally very different from traditional coherent links, where the DSP has to do a lot of heavy lifting to compensate for dispersion in the fiber. We also want to exploit as much as we can in terms of degrees of freedom to maximize the bandwidth per fiber. So you have the 2 quadratures, 2 polarizations, and I'll show you that link architecture. The exciting thing about coherent, and I think, again, this is different from why it was put into the long haul networks in the first place, which was really more of a spectral efficiency motivation, is the expanded link budgets that you can get. Theoretically, you can get improvements of factors of 100 in sensitivity versus direct detection. That's against NRZ direct detection or OOK direct detection. It's even better when you compare it to things like PAM4. But that extra sensitivity, if you design it right, can translate into extra link margin, which then can start opening doors to new functionalities in the optical domain in the networks. So we're talking about wavelength selective, either routing or switching. And I'll sort of finish the talk with visions of that. But I think that's a very good companion piece of technology to just moving to coherent links. So here's the snapshot of what we're working on. We're working on single wavelength versions of this as all of our demonstrators in the program. But fundamentally, we've been at 200 gigabit per second per wavelength targets throughout the program. And I think it was an ambitious target, especially when you see that we conceived this about 5 years ago. And the good news is we're getting there now. So I'll show a few pieces of data or a few snapshots of hardware that are operating at 50 gigabaud level. And so I think we're within touching distance of that 200 gig link shortly. The basic architecture relies on an optical phase lock loop to lock both the frequency and phase of a local oscillator in the receiver to the incoming signal. This was an idea that was really, I think, pioneered back in Larry Calderon's group of more than 10 or 12 years ago. And they showed with working hardware that if you use the optical phase lock loop, you can have direct outputs of the receiver at error rates that are less than 10 to the minus 12. So it eliminates the need for FEC and the added latency there, or for any additional DSP processing. Polarization recovery is another feature that we're implementing in the optical domain. This also offloads a function that's usually done in DSP for more conventional or longer haul coherent technologies. And so what I would say is our architecture is fairly standard. We have an IQ modulator to do QPSK modulation. I'll tell you why we're doing that. We do want to support multiple wavelengths to allow bandwidth scaling at that 200 gig per wavelength granularity. The unallocated link budget is, turn the pointer, is the key. We want to unlock this so that we can potentially do interesting things in the optical domain. And then on the receiver side, it is a relatively conventional architecture with the exception of the OPLL feedback loop to control the local oscillator and the optical polarization recovery for polarization demultiplexing. I would say our view of analog coherent, we've used that term and we've used it because you could potentially have no DSP. We're evolving in our thinking with that. So I think where we're really going is not necessarily to have complete religion about no DSP whatsoever, but in the future, trying to find the best implementation space for the function at hand. So working on seeing whether or not it makes sense to do some things within the electronics domain, or if we can do it more efficiently in the photonic domain. And so that obviously the last bullet demands this sort of holistic view of the link itself, and really sort of tight integration of the design efforts for electronics, photonics, and packaging. So this is kind of a generic chart, but it looks kind of like a workshop chart. So maybe it's helpful to motivate some discussion. But when we're looking at how to scale bandwidth, there's the trade-offs to be made. And the primary one I think you start with is the symbol rate. This is usually limited by how fast your electronics and photonics can go, your packaging limitations. In reality, I think it's dictated by SerDes in today's world. And maybe to start that point of discussion, SerDes are there for a reason. They get a bad name, but they're there because pins are expensive. Electrical pins, optical pins. So it's not that we made a bad choice and have been on the SerDes roadmap forever. There's really good reasons why it's there. And I think that's here to stay and will continue to drive us forward. But again, so you go up in symbol rate as high as you can. Your next axis is you can try and put more bits per symbol. And as you climb that ladder, it's just more complex. So generally it translates into higher power consumption, higher latency, because you sort of have to unravel a lot more things. And so more FEC, more DSP, more linearity. And so it's just a more complicated design space. And where we are, I said, is QPSK. We see that as kind of the threshold of least complexity as you try and enter into the world of more higher order modulation formats using both amplitude and phase. The other axis is, and I think we've heard a lot about this today too, is just scaling kind of the parallel channels. That could be parallel wavelengths, that could be parallel fibers. Neither one of those comes for free. So I think there's still huge challenges in trying to get high fiber counts attached to chips. Again, we've heard about that all day today. They raise issues of loss, the tolerance of the assembly, the uniformity, the yield. And then WDM is never free. There's operation over temperature that needs to be considered, stability, added losses of the multiplexing components. So none of these sort of come for free. The point I'll finish with, though, is when we looked at it from the standpoint of, well, if we choose a link architecture, what would let us do innovative things in the network architecture? We landed on 200 gigabit per wavelength because it seemed a good trade-off in terms of not going too far on either of the axes where you can't partition your granularity into any smaller values. So if you go up in symbol rate or you go up in bits per symbol, you basically have to receive the data before you can break it apart. So if we pick a reasonable spot there and then scale bandwidth by adding parallel lanes, either wavelengths or fibers, we think that opens up a lot of possibilities. And you could just see it, the math's simple, but for a 51T switch, if you're at 800 gig granularity, you get 64 ports, you get a factor of 4 better if you're at 200. So if you can exploit that in the network design to make the entire system more efficient, that's a lever that we'd like to pull. So quickly on this one, why did we land where we are? So there's a great paper that came out from Google, I guess it's almost 2 years ago now, 2020. But the thing that was a kind of surprising takeaway was that if you scale to higher order modulation formats, you can end up doing worse in terms of link budget than the PAMs, the PAM4s, the PAM8s, unless you have a lot of swing on the transmitter. And what that translates into is if you need a lot of voltage swing on, this is an MZM drive voltage, it translates into high power. So you got to be a little bit careful. Coherent doesn't necessarily mean that you get higher link budgets. We took that framework and replotted it, but there's no QPSK on this initial plot, so we added it. So there's the 16 QAM curve from up here. You can see right off the bat that QPSK gives you a lot of extra link margin to play with. And again, we see that as a very key factor because we want to do things with that margin in terms of putting in wavelength routing or switching. And you can get that extra margin without having to go to the very highest drive voltages. So there's an efficiency win as well. We've modeled these coherent links, have a paper that came out last year, and we think that it's sort of in the realm of 5 to 10 picojoules per bit that could be possible. And that's including 13 dB of unallocated link budget. You could, again, use for doing interesting things in the photonic domain. So it's kind of the summary. Why did we pick 200 gig per wavelength? We like the granularity. QPSK gives you link budget and efficiency. And the nice thing about QPSK is it's basically the same electronics as NRZ. So by the time you go through the hybrid and you've separated I and Q, you're making hard binary decisions, ones and zeros, just like you would do with limiting amp, very efficient NRZ-based electronics. We can get low bit error rates. So if we're really concerned about latency, we can avoid any post-processing that would add to that in terms of forward error correction. And I think I mentioned the granularity. So just again, a couple snapshots. I'm not going to go into a lot of details, but we spent a lot of time developing a platform that was capable of sort of hitting the rates that we think are relevant, which today it's, I think, 50 gig and 100 gig is coming soon. So this is 108 gigabit per second data for some of the electronics chips and packaging, and an example of one of our coherent receivers that's based on a phase 1 design that we designed in Global Foundries 90WG photonic technology. So we've cranked up the platform. This is an electrical only eye diagram up to 108 gigabits per second. We've shown several at this point 100 gig coherent receivers working. They both, what I'm showing here, use that first generation PIC. And we test it in a self-homodine configuration because we don't have an integrated LO in that particular photonic integrated circuit. Using SiGe electronics, I think I forgot the picojoules per bit. This is about 3 picojoules per bit for 100 gigabit full receiver. And this is in 45 nanometers, we were able to turn that down even more. So this is a full, again, 100 gigabit per second. So this is 50 gigabaud. It's a dual pole PIC. We're only testing one polarization here, but less than 100 milliwatts of power consumption. So less than a picojoule per bit for that complete receiver at 100 gigabits per second. I'll shift gears now and just spend a minute on the new architectures that are enabled by that extra link budget for that we get by choosing the right brand of coherent detection. So this is a slide from Adel Saleh. He's leading our network architecture design for the program. And you could read these words. If you work with Adel, you'll realize quickly that he's a master of PowerPoint. So this is sort of the one that has some explaining words if we're sharing slides. I like the colored ones better. So in this case, the idea is that if we have extra link budget, we could insert an optical routing layer somewhere in the stack, and it could be above top of rack. I think Adel's looked at it, and it's sort of flexible where that has to go in terms of the typical hierarchies. But the AWGR would just basically be a play to increase the radix of the switches. So it would be able to separate those 200 gigs per wavelength and add better scalability to the data center. The future vision we want to work to is something like this picture. where we could configure with a reconfigurable photonic switch the connectivity that we wanted for different jobs. So I think this brings up the sort of concepts of disaggregation, configuring the network connectivity to the workloads at hand, maybe training for machine learning. But it basically would give us a lot more flexibility. The network would turn from being something that's fixed and hardwired to something that we could reconfigure when we wanted it to. And we're not necessarily talking about fast optical switching. This isn't packet level. This would be something that could be relatively slow, but again, give us what we think are key features that will allow us to improve the efficiency of the network and of data centers as a whole. So I'm coming to an end. I wanted to put in acknowledgements because I think it's important enough that I'll throw it in before the summary thought slide. But definitely, I showed a snapshot of what we're working on. It's enabled by a bunch of talented folks working together. I would say that the students are at the bottom of this list, but in some ways that's turned on its head. They're the engine that makes these things go. But again, very honored to be able to work with all of these folks. And then closing thoughts. So when we first started saying this 5 years ago, that Coherent was coming and trying to pitch this story, I think we sounded a little bit crazy, but I think the reality is it's coming now, and the industry realizes it. It's likely primarily driven just by bandwidth and trying to meet the bandwidth needs of the links. But the link budget should really be recognized as a key feature to exploit and as a key enabler of maybe doing these more interesting things like having reconfigurable photonic networks. It's going to be difficult for just evolving or an evolution of conventional coherent technologies, the sort of DSP, even DSP light coherent, to meet what we think we need for future data centers in terms of efficiency, density, and latency. We think we can make coherent compatible with co-packaging. I haven't really talked about that too much. There are challenges in the density and the energy efficiencies. Primarily, as I say here in the transmitter, what's kind of surprising is you think the receiver could be the power hog. It turns out for us, it's the transmitter where we think we need to spend more work. And then I would say at the end, new results coming soon. So we're happy to have Intel as a partner. It's perfect for this vision because their technology offers integrated local oscillators. They have that hybrid laser technology where they can integrate the laser straight into the die. So we're in the middle of testing our first assemblies. I think we've in our first round of receiver testing, we're seeing speeds that are higher than anything that we've measured before. So very promising data, and I would say stay tuned. We'll be hopefully presenting and publishing that shortly. And I'll end there.
Great. Thank you very much, Clint. Great presentation. We had one question that came in on the chat from Chris. Chris, do you want to unmute and ask your question directly? Or I can ask it for you.
Sure. Yeah, that is really nice work, Clint, as always. What is the architecture of your polarization controller? How much die area does it use? It's kind of a critical element.
Yeah, that's a good question. So the typical architecture, and I should have thrown out that another key person working on this kind of realm of analog coherent is Joe Kahn at Stanford. So he's actually got some great papers that explain sort of the inner workings of how you can do these. In one of his papers, he shows the basic 3-segment.
Okay, you're doing what Joe is doing.
Yeah,
this thermal kind of rotator thing.
So yeah, there's phase shifters, a Mach Zender that gives you a weighted summer and an additional pair of phase shifters.
And it's thermally controlled.
It is thermally controlled, and I think that is a challenge because those tend to stretch out. We've done them kind of. We did actually work on this. We made custom heaters in the process we were working in to try and shorten that up. But that polarization control, it's a tough one because I think the DSP does it very efficiently. So this is another area where I think we'd really have to take a hard look at that and say, where is it worth doing in both area and power in the optical domain, or doing it more conventionally in the digital domain.
Hey, since I got you before Rob cuts me off, why do you just insist? I mean, we're in full agreement that if you need the longer link budget, Coherent's great for that. But if I look at your energy results from your first chip that came back, I mean, that's very interesting, even in a conventional low link budget application, right? Am I reading that wrong? But this seems very interesting, even for mainstream. You don't have to tie it necessarily to these interesting optical high loss switching applications?
Yeah, no, thanks for that question, because that's another key advantage that we wanted to say is you can, in some ways, tailor the power that you have to spend on the link to the link budget that you need. And so, sort of notionally, you can say, I can turn down my local oscillator and maybe my source laser if I don't need that 13 dB that we're trying to get to enable photonic switching. So I think there's a lever to try and get even better efficiencies. And again, yes, I think we focused because we think there's a big story in trying to enable photonic switching. But I think you bring up a great point, because if you don't need it, there's probably further optimizations that you could get.
Very nice. Thank you.
Thanks.
Great. Thanks again, Clint.